or it won't be a full period's worth of a lecture, okay? All right, so let's do 5.6. This section is called the fundamental theorem of calculus, and of all the names of theorems that we've gone through so far, this sounds the most prominent. And it is. It is a huge part of this class, but it's, in my opinion, it's a pretty simple theorem. There's the fundamental theorem of calculus, and then there is the second fundamental theorem of calculus. That one's a little bit more arbitrary in nature and a little more difficult. We'll cover that maybe next week or on Friday. We'll just see what I get to and when I get to it. Probably Friday. But either way, let's talk about the last page of the test you guys took on Friday. What was on that last page?
I don't remember.
The area one, the limits of a sum, right? And what you're doing is you're finding the net signed area between the function and that curve, okay? How long did that problem end up being? For the ones that we've done, it wasn't bad, but still longer than any of the other ones on the test, right? 10 steps or whatever it was. It was a lot.
Yeah, I did it wrong.
Oh, no. But either way, that one probably required the most work out of any of them. But either way, finding that area was a lot. There was a lot of things you had to do. Break it up in limits and of sums and stuff like that. So instead, this is the way that I told you guys a week and a half ago that is much faster to evaluate area under a curve. Okay? It's called fundamental theorem of calculus. All right, and it says this. If your function's continuous on a closed interval, and if f of x is any antiderivative of f on the interval, closed interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, which says this. You find your antiderivative, and then you plug in your limits and take the difference between the two. So you plug in your top limit, and then you subtract off what you get when you plug in your bottom limit into your antiderivative. What letter do you notice is missing that we've dealt with integrals in the past? C. There's no C there. It's not necessary. Let me show you why. Let's do this first problem. You'll often find that the notation that I will use when I write this, integral from a to b of lowercase f of x dx, whatever, is equal to capital F of x and then evaluated from a to b. So I will typically find my antiderivative. I'll take that step to find the antiderivative, and then I'll write it typically with a bracket or just a straight line with the limits attached to it, just to remind myself that I need to evaluate my integral with those limits, okay? All right, so let me show you why C isn't necessary. I'm going to include C when I find my antiderivative for this first one, okay? All right, antiderivative of x is what? There it is. And then I'm going to put plus C. Like I said, I don't need it. I'm just going to do it for this one example, okay? And then I'm going to evaluate it from 1 to 2. All right, let's plug in our limits and see what we get, okay? So I'm going to plug in my limit for 2 first, so evaluate it when x equals 2, and then subtract off what I get when I plug in 1. So then I would have 1/2 2 squared plus c. So here's a 1 piece minus, and then I'm going to put this all in parentheses, 1/2 1 squared plus c. I don't really need those brackets there. I'm just kind of doing it for aesthetic purposes, I guess. All right. First of all, what happens to my C's? They cancel, and think about it, they would always cancel, right? Because when you would evaluate it with your limits, your first one would be positive, and then you're subtracting off your lower limit always, and it's always positive inside that parentheses, so your C's will always cancel out. So because of that, I will never write the C when I'm using a definite integral, okay? So instead, I just get, okay, so let's see, 4/2, which is 2, minus 1/2. Don't know what happened there, 1/2. So then I end up with 3/2 as my area under the curve. Other ways we have found the value of this integral is we have drawn a picture. And then we would find our geometric area. I mean, we very quickly find out that, like, you can't always do that because we don't always know the geometric area. But in this case, what would the shape of this figure be under that curve? Yeah, so if I did want to find the area of that trapezoid, I could. 1/2 times base 1 plus base 2 times my height. You'll see that I get 1/2. Base 1 is a height of 1. Base 2 is a height of 2. And then the height of my rectangle, or my rectangle, but my trapezoid, if I rotate it, is just 1. So you would still end up with 3/2. Okay, so your area is the same regardless. However, like I said, we can't always find the geometric area, okay? Because it might not lend itself to be a figure that we are familiar with. All right, okay. Let's do some more examples. For example, this first one results in an area that I wouldn't have the formula for. So it's 9 minus x squared, not square root of 9 minus x squared, because that would be a semicircle. But instead, you know, my function would look like this. No, that looks terrible. Something like this, okay? And I don't have a formula for this parabola, like a formula for the area of that parabola, okay? So instead, let's use fundamental theorem of calculus to actually evaluate our antiderivative, our definite integral. All right, so we take the antiderivative of each piece, which would give me 9x minus open-ended. What's the second part of that? Oh, no. What's our antiderivative of x squared?
1/3 x cubed.
There it is. Yep, and I don't need the plus c, so instead I'm just going to write it with my limits of 0 to 3. And then I just need to plug in my limits. Top limit goes first. 9 times 3 minus 1/3 times 3 cubed. Minus, and then I'm going to put 0 in parentheses. So 9 times 0 minus 1/3 times 0 cubed. And then we evaluate. So 9 times 3 gives me 27, minus 3 cubed is 27, but 1/3 of that would be 9. Minus, wow, it's dramatic. And then inside that parentheses is just all going to be 0, right? So it's kind of nice. So then I get 18. Okay. All right. How are we feeling? We all right? Nice way to come back on a Monday after a weekend, doing these simple antiderivatives, hopefully. Hey, let's do some trig, though. I know you guys love trig. All right, let's draw a little graph. The graphs aren't necessary, but I find that mathematics is so much easier to understand when you have a visual with it. You guys remember what the graph of cosine looks like? Where does it start? At 0.
1.
Yeah. And then what about pi over 2? What's that output?
0.
Mm-hmm. So then it's going to look something like this. Maybe with more curve, though. Maybe not that much curve. But either way, you get the point. Okay. So I need to find the area under that curve. All right, antiderivative of cosine. Mm-hmm. And then I just need to evaluate that from 0 to pi over 2. Sine of pi over 2 minus sine of 0. What's sine of pi over 2? 1 sine of 0?
0.
Great, so I get 1 as my area. Cool. All right, let's keep it moving.
What is unit square?
That's a good question. It's just saying finding the following values, so it's not putting it in context of area. So no, you don't need to put unit squared. Now, if in your instructions it said, hey, find the area under the curve,
Okay.
then since they put it in context of area, then we would, okay? That's a really good question though, Soph, and that's a really good question, Ellie. But either way, these are just, it's just represents values, okay? We could think of that value as the area under the curve. But unless they put it in that context, then we don't need to, okay? All right, let's keep it moving. What do you want to do for the first one? Skip it. Rohan wants to skip it, so. All right. For the next one, we got to use trig. All right, so it's secant tangent. Can we take the antiderivative of secant tangent?
Yeah.
What is it? Nice. And then we want to evaluate it from 0 to pi over 3. All right, secant pi over 3 minus secant of 0. I don't know. I think of secant in terms of cosine. So let's see. Pi over 3 is yonder with my values of 1/2 square root of 3 over 2. And then 0, of course, is here with my values of 1, 0. Okay, so 1 over cosine pi over 3 minus 1 over cosine of 0, which would give me 1 over 1/2 minus 1 over 1, giving me a value of 2. What'd I do?
1 over 1/2 is 2. 2 minus 1 is 1.
Oh, there's a 1 there, isn't there?
Yeah.
All right. I just wasn't done writing. 2 minus 1, and then we get a value of 1. There it is. Yep. Rohan, do you, are you ready to go back to it now?
Sure.
Okay.
It's fine.
All right, it hasn't gone away, despite being crossed out. What do you guys want to do? You said what? I heard some things. I like Benny's option, but I also heard U sub, right? So we just came out of doing a bunch of U sub on your test. If you did U sub, you'd let U be X, and then you'd have to, change your variables in order to do that. But the easiest way to think about it is what Benny said. Let's just combine these values here. So 4 to 9. So what's that going to be inside of my integral? X to the, this is just X, yeah, 2.5 or 5/2 dx, okay? Now, that begs the question, can we do U substitution with definite integrals? Absolutely. And that's what I'm going to teach you guys on Wednesday when we're all back together, is how to do U sub with definite integrals. It really does not change much. There's an extra added caveat that I want to teach you guys about, but it doesn't change much. What's my new exponent become? 7/2. So my scalar multiple is 2/7. Then I evaluate that from 4 to 9. So there's a few ways you can write this. You could put a 2/7 on each piece, or I'm going to put a 2/7 in front, and then I'm going to put my evaluation in a set of parentheses. So I'm going to have 9 to the 7/2 minus 4 to the 7/2. Granola bar is talking back at me now. All right. Hey, let's be smart about this. I want to take 9 to the 7/2 power. Do you want to take the square root of 9 first, or do you want to raise it to the 7th power first? Square root. Okay. So now we're going to have 2/7 times 3 to the 7th. I don't know what that is. And then same thing with a 4. Square root of 4 is 2, so I'm going to have 2 to the 7th. I know what that is. 3 to the 7th power. That's 2 to the 7th.
Oh,
Well, I'll write it in there just for you, Azra. 128. But we need 3 to the 7th. 2180. I think it's 21. Is it 2187? Never doubt Rohan. Should have known. Cool. So 2187 minus 128 gives me 20. Yeah, okay. So then if you double that, you get 4118 over 7, I think?
Yes.
I think that math is math. Cool. Which I'm going to assume is relatively prime. I think there's a division rule for 7, but I just can't remember what the rule is. The only one I remember is 9. If you add all the digits in a number together and it's equal to a multiple of 9, then it's divisible by 9. Do you guys know that? All right, cool. I think on the next slide, your instructions are weird. Doesn't it say to find like the geometric area on the next slide? Yeah, I just erased that and wrote find. Yeah. Yeah, so we have to do the real thing. We're not going to use geometric area. I just copy and pasted it from another numbers file, and then I forgot to change the instructions for that one. So just want to find the value. All right, more trig. What do you want to do for the first one? Let's take the 5 out. So it's got to go out in front as a fifth. And then 0 to pi over 2. Sine of x is left over on the inside, dx. Antiderivative of sine. Good. Negative cosine of x. We want to evaluate that from 0 to pi over 2. If you want, you can lump that negative from the negative cosine with the 1/5. So make it 1/5. And then we evaluate positive cosine inside that parenthesis. So cosine pi over 2 minus cosine of 0. What is cosine of pi over 2? 0. Good. Cosine of 0? 1. What's up, boys? All right, so what do we get? We got a lot of them, eh? Is there any more?
No, that's all.
Thanks, guys. All right, so negative 1/5 times negative 1 gives me a fifth. I juked you. I didn't mean to. I'm sorry.
Just to check it. Fuck you, what?
For real life? Boys, I'll tell you the same thing I told everyone else. The ground is not cold enough yet. Really, the roads aren't cold enough yet.
That's the issue. It's driving me crazy.
Do what?
That's what my dad told me this morning. He said, the roads are still warm.
Yep.
And the ground is still warm.
Your dad's right.
Doing that? Cool down. It's
Yeah,
like, stop. Let's take a
It was like 50 degrees yesterday, man. Fifth. Machi? I don't know. What does it say? Does it say teacher's convenience? There will be time at the end. Okay.
quick.
Trust me, guys. I know you get excited about a snow day,
We never played a game though.
but you have no idea how excited I get about a snow day.
Oh.
It's the best.
Why do you get so excited?
Cuz.
Other teachers.
Yeah. No, if we have a snow day, I mean, it's just me at home with my kids, and I don't do work when they're awake. So it's like, I would have to wait till they go to bed anyway. So it doesn't affect that. But then they get an extra day off. It's amazing. I love it.
Wait, but what if they have a snow day and you don't?
Oh, then they're going to school, and I'm going to get stuff done at home. That's what's happening. Although.
They have a snow day and you don't.
Oh, woof. Oh, they still go to Grandma's house. So they'll hang out at Grandma's house. It's all right. Okay. I'm just going to be really jealous and say a lot of things about it under my breath. But okay, here we go. Integral from 0 to pi over 2 of secant squared x dx. You guys had more snow up here than I had at home, though, for sure.
You said what?
You guys had more snow up here than I did at home.
Where do you live?
I live in Barberton. So it's like 25 minutes south of here. So south, southeast, something like that.
Where do your kids go to school?
Barberton. Yeah. Barberton, yep. All right, tangent pi over 2 minus tangent of 0. Pi over 2's up here. That's 0, 1. Uh-oh. Undefined. Our function is unbounded. So we cannot find our value, okay? My function is not continuous on the interval from 0 to pi over 2, so we cannot find the value of our integral, okay? Because our function is unbounded. No solution. Maybe my kids will go to Revere one day.
They should.
Maybe. Revere's a great district. That's why I'm here. Because I wanted to be the top.
Yes. Top 20, top 30.
We're up there.
It used to be the top 10.
When we were in like 7th grade, it was in the top 10. But then it went down from there.
All right, so this is not a typo. I did mean to include that integral twice. Reason why, what pops in your mind as soon as you see this? What should I do?
Negative. I don't know.
Yeah, flip them with a negative, right? Because it's weird, those limits, the bottom limit is, further to the right than the top limit, okay? So what I wanted to do is I wanted to do this twice. I want to use my property of integrals to flip it and put a negative in front, and then show you it's the same thing as if I evaluate it without doing that, okay? All right, so you want to do the property of integral way first?
Yeah.
Okay, so negative in front, and then my limits would be, my lower limit would be 1, and then my upper limit would then be 4, x squared dx. And then we evaluate. So I have that extra negative in front, and then I get 1/3 x cubed evaluated from 1 to 4. So negative 1/3, I have 4 cubed minus 1 cubed. 4 cubed is 64 minus 1, which gives me negative 1/3 of 63. What is 1/3 of 63? $21. So negative 21 is my area. All right, let's do it where we ignore the property and we just evaluate it as if we would have normally. So we get 1/3 x cubed evaluated from 4 to 1. All right, well that's just 1/3 times 1 cubed minus 4 cubed. 1 cubed is 1, 4 cubed is going to give me 64 again. So I would get 1/3 times negative 63, still resulting in negative 21. So you get the same thing either way. The interesting thing about this is our area we ended up with was a negative value, although my function lies entirely above the x-axis on this interval. The reason why that happens, so I'm finding this area here, instead of, like if you think about it in terms of a rectangle, instead of my heights being negative, what is happening is actually my base is negative. Because when I do my evaluation of my integral, instead of doing my top limit being 4 minus my bottom limit, so 4 minus 1 would give me a positive value, I'm actually doing a base of 1 minus 4, so I'm subtracting, which gives us a negative base. Now, you still have, again, this area, but since our base was thought about it from a negative perspective, I get a negative value for that. Okay? All right, cool. Hey, properties of integrals for the last one, though. 0. Soph she had that on the ready. It is 0. If you think about the graph of something like that, 1 is here, still looks like this. It's just this sliver, and there's no dimension. It's, it's one dimension, so it's not going to have an area. Okay. All right. Cool. Hey, piecewise function. I don't think we've done any integrals of piecewise functions yet. We did derivatives, though. When we did derivatives of piecewise functions, oftentimes we took the derivative of each individual piece, right? Integration, we're going to do something very similar. We just have to integrate it piece by piece. But before I do so, I need to ensure that my function is continuous. So, is f of x continuous?
Yes. I don't know, actually.
Kira doesn't know, so let's find out.
It's given up.
Is it giving continuous vibes, as the youths say? Okay. Oh, it's just giving? Got it. I need to find out if f of 2 equals the limit as x goes to 2 of f of x. That's how I figure out if this is continuous at that point. Okay? All right. So first of all, what is f of 2? Well, I'd have to plug it into where it's defined, which gives me 4. The other thing I need to find, in order to figure out what the limit as x goes to 2 of f of x is, that really means I should find the limit from the left and from the right. Good. So limit as x goes to 2 from the left of f of x, and then I want to find if the limit as x goes to 2 from the right of f of x, if those limits exist, and then I'm hoping that they equal 4. All right, from the left, that would be into x squared, right? So then 2 squared is going to give me 4. Nice. 2 out of 3 ain't bad. And then if I plug it into the bottom, well, that's how I found the evaluation in the first place. So it's going to give me 4, of course. So f of x is continuous when x equals 2. So I can proceed with taking my antiderivative. But I should do so in pieces. So really, I should do the integral from 0 to what? 2 of what goes inside there? Good, Kara. Here, x squared. Sound like I said Kara there. I know your name's Kira, I promise. And then what's the limits for the last one? Yeah, and then my other function. 3x minus 2 dx. Now I have to evaluate each piece. All right, so the first piece, I'm going to get 1/3 x cubed, evaluated from 0 to 2. My second piece, take the antiderivative of each one of those values, would give me 3/2 x squared minus 2x. That gets evaluated from 2 to 6. We're going to do this in colors. All right, so I'm going to toss that 1/3 in front of a set of parentheses. And then in the inside, 2 cubed minus 0 cubed. Plus, let's write the rest of this in red. All right, there's going to be a lot to write here. So 3/2 times 6 squared minus 2 times 6 minus another set of parentheses. Plug in 2. 3/2 times 2 squared minus 2 times 2. It's a lot to evaluate, but sometimes it's nice to write everything out because you'll find that oftentimes when you're doing definite integrals and you've got more complicated functions, sometimes things cancel out or combine easier than others. The blue part, though, I'm going to get 8/3. There's really no way around that. And then for my next trick, let's see. 6 squared is 36. 36 times 3 is 108. Half of that's going to be 54. Minus 12 minus my parentheses. All right, so 2 squared is 4. Half of 4 is 2. 2 times 3 is 6. Minus 12. All right. So let's see, those 12s cancel out, right? So 54 minus 6 gives me 48. Oh, what did I do?
It's minus 4.
It is minus 4. Where did the 12 come from?
I don't know. I think you just kind of did it.
My imagination. My math imagination. All right. Well, then in that case, it's 54 minus 14, which gives me 40. So 8/3 plus 40. Brother. Why? Please. Oh, thank God. All right. 8/3 plus 40 is going to give me 128/3. And those are relatively prime numbers. So 128/3. All right. Questions there? Not yet. Una más. All right. Example 6. Now, notice I changed my file compared to your file. So that bottom integral, what I want you guys to do is to, because there's absolute values in that integral that's in the bottom, either cross them out and change them to parentheses, or double tap and go into LaTeX and then change them to parentheses instead of absolute value. But they should be parentheses down there. Okay, sorry about that. So right there. Okay. Okay, we did net signed area, and that's what that value represented on the back page of your test was that net signed area problem. We talked about how you can have positive area and negative area, and when you're evaluating it, if you have negative area, it just cancels out some of the positive, or your whole area could be negative in general, okay? So because of that, if the question asks you to find the total area, then that means you're working with absolute value, okay? It'll take those negative values that go below the x-axis, pop them above the x-axis, and giving you a positive area. Okay, so that would represent total area is ensuring that all of our values are positive. Okay, so when we find total area, use absolute value. Okay, so for the example down below, we want to find both net signed area and total area, which means we're going to do the integral as normal to find our net signed area. And then when we find our total area, we need to make sure that we use absolute value. So we're going to do 2 of them here. All right, and then we'll do a graph of each one. All right, so antiderivative of 2x minus 5. We'll just do this just as we did all the other examples. So x squared minus 5x, and I want to evaluate that from 1 to 5. All right, which gives me 5 squared minus 5 times 5. And then minus 1 squared minus 5 times 1. The first set of parentheses is just 0. And then minus negative 4, so giving me an area of 4. All right, so that's my net signed area, positive 4. Now, let's find our total area, okay? So again, what I then need to do is my same integral, but my function needs to be inside of my absolute value, just ensuring that I don't have any negative area. There's a couple ways we can go about doing this. How did we approach absolute value in the past? Piecewise. So let's do that. So let's say f of x is 2x, absolute value of 2x minus 5. Let's break it into a piecewise function. So again, the only difference aside from 2x minus 5 would be an extra negative on that function, right? But we got to find where our domain splits at. Where will my domain change, or will my function change from one to the other? At what x value? 2.5, 5 halves, and where'd your girls come up with that?
Where it equals 0.
Yeah, so where the inside of that absolute value equals 0, that's where my domain is going to switch, okay? So 2x minus 5 equals 0. That's where the girls ended up with 5 halves. Okay. All right, so which one's which?
The bottom is greater than 2.
Good. So I'm going to say strictly greater than 5 halves, and this one would be less than 5 halves. And you can do that by testing values. Now, Kira mentioned greater than or equal to. I'd be fine if you put it there. The other way that we could do it, which would be a little more formal, what happens when x equals 5 halves? What's your output? Yeah, so if you want, you could think about it like a third case. When x equals 0, or your function equals 0 when x is equal to exactly 5 halves. Either way, now we have a piecewise representation of our function. So how should I go about evaluating this integral? What do you think? We built a nice continuous function here. So I say we evaluate it, split it up into multiple integrals. So what would the limits of my first integral be? From 1 to 5 halves. All right, and then when it's 1 to 5 halves, I want to use this top function here, okay? Are you guys cool if I just write 5 minus 2x inside there? Are you all right with that? Distributing the negative and then reordering the terms, dx. Okay, and then plus the integral from, what are my other limits going to be? 5 halves to 5 of 2x minus 5 dx. So now I have to evaluate both of those. But I believe. So 5x minus x squared evaluated from 1 to 5 halves. And then I have to add to that x squared minus 5x evaluated from 5 halves to 5. All right, it's 4 things I got to plug in, so that's a lot. Okay, so if I plug in 5 halves, 5 times 5 halves minus 5 halves squared. There's my first piece. Minus what I get when I plug in 1. So 5 times 1 minus 1. All right, so that's that first piece. Now let's do the second piece. Big parentheses. 5 squared minus 5 times 5 minus what we get when we plug in 5 halves. So 5 halves squared minus 5 times 5 halves. Lots of parentheses. This is what I mean by just evaluate all the pieces as they lie, because you'll find out that oftentimes in situations like this, things cancel out or combine nicely. So 25 halves minus 25 fourths, and then minus 5 minus 1 is going to be 4, plus this piece is going to be 0. You guys with me there? Those things cancel out, so I'm just going to let that happen. And then the last piece would be negative 25 fourths plus 25 halves. And then let's see, there's a lot of repetition there, so let's see how my things combine. Well, I know if I combine negative 25 fourths with negative 25 fourths, that's negative 25 halves. Do you guys agree with that? So that's going to cancel out one of my 25 halves. So then I just have 25 halves minus 4. So 25 halves minus 8 halves gives me 17 over 2. So that's like 8.5, yeah? So how did my total area compare to my net signed area? It was more work, but it was larger, right? Okay. Let's look at what's happening on a graph. All right, so our function was what again? 2x minus 5? All right, so 2x minus 5, and we were working from like, what was it, 1 to 5? Yeah. So 1 to 5. Okay, and then if I plug 1 in into 2x minus 5, then that would give me negative 4. do this in red. And if I plug 5, that would give me 2 times 5 is 10 minus 5, so then 5. Okay, so my function looks like that. I missed the mark a little bit. Okay. All right, now, if I went to find my net signed area, it would be the area of this trapezoid, which would be not trapezoid, triangle, which would be negative, plus the area of that guy would be positive. And we see that there's more positive area than there is negative area. So me ending up with a positive result does not seem far-fetched at all. However, if I'm doing absolute value, then I am going to, oh, you hate to see it. If I'm doing absolute value, then my graph is going to split up like this. And instead, this area above my x-axis would be positive. Okay, so my total area would be the combination of this piece and that piece. All right? Feeling okay? Okay, cool. Your homework, which I want you guys to spend the rest of the period working on, is 1 through 20, 23A, 24A. So a lot of definite integrals along the same vein of what we've done. So as a reminder, tomorrow we will come in and we will review your homework for this, okay? I will teach a section on the beginning of 5.7, which is motion. And then Wednesday we'll come back and we will review homework for motion. We'll do 5.8, which is just this with U substitution. And then on Thursday, we'll review the homework for 5.8 and we'll quiz on what I just taught you today and then also this with U substitution, but not motion, okay? And then we'll do motion and then second fundamental theorem of calculus and then mean value theorem for integrals and average value on Thursday, Friday. Cool? Quiz on Thursday, young lady. Couple times. But you're with it now?